Welcome to the sixth lecture from chapter number 7, VLSID design. In this lecture, we are going to study rise time delay for a CMOS NOT. In our last lecture, we studied an expression, we derived an expression for the fall time delay of CMOS NOT. Right, traditionally, the rise time delay is computed like it's the difference between the time when the output has risen to 90% of VDD minus the time it was at 10% of VDD, dy minus dx. We saw a similar expression in our last lecture when we studied the fall time delay. So this is time versus V of t, the voltage, and we are interested in this time in the difference of dy and dx, and we declared that as the rise time, right? So let's move on and find the expression, a general expression for t for this curve, for this plot. For that we'll have to go back to the linear circuit analysis course that we studied in the first in our first semester. V of t is VDD, the maximum voltage, times e to the it's not e to the minus, it's 1 minus e to the minus t over tau p, right? So this is mathematical expression, the mathematical expression for this curve, right? And this is the way this C out is charged through this Rp, and this tau p time constant is Rp C out, because the outward capacitance it charges through Rp. That is why we have written tau p as Rp C out, and it happens when the input is logic 0 and the output is going to be logic 1. I haven't drawn the full circuit, it's only part of the circuit that comes in action when the input is logic 0, the input of CMOS NOT is logic 0, and we are going to have logic 1 at the output, right? So the next task is to rearrange terms on this expression to bring t on the left hand side and everything else on the right hand side. That we can proceed by dividing this, and now we have this 1 minus something here, so we can take e to the minus t over tau p on the left hand side is equal to 1 minus, and this ratio on the right hand side, v of t over vdd, right? And then we can compute log on both sides, so minus t over tau p, because log cancels with this e, this is log of 1 minus v of t over vdd, and t is minus tau p times log of 1 minus v of t over vdd. So this is the expression that we were looking for, t, v of t in terms of t on the left hand side, everything else on the right hand side. Now we know what dy is and what is dx. Dx is the time when v of t is 0.1 vdd. So we can write dx as, we can either write dx first or dy first. So let's write dx is minus tau p log of 1 minus v of t at dx is 0.1 vdd, 0.1 vdd divided by vdd. So this cancels, and we are left with dx is minus tau p log of 1 minus 0.1, it's 0.9, and then we can write dy as minus tau p log of 1 minus v of t is 0.9 vdd at dy, 0.9 vdd VDD over VDD. So this becomes minus tau p log of 1 minus 0.9, it's 0.1. So these are the two equations we need to compute TR. So the rise time can now be computed simply by rise time TR can be computed as dy minus dx, where dy is minus tau p log of 0.1 minus dx is minus tau p, so minus time minus becomes plus tau p log of 0.9. Now we'll use the same expression, that log of a minus log of b is log of a over b. Log of a minus log of b is log of a over b, this one. So we can compute, first we can compute dp, we can take dp as common, and then we can write log of 0.9 minus log of 0.1. So now we'll apply that log of a minus log of b is log of a over b, so log of 0.9 over 0.1. Okay, tau p is log of 0.9 over 0.1 is log of 9. Log of 9 is 2.2. So the general expression for TR for CMOS NOT is 2.2 tau p, and we studied in our previous lecture that TF was 2.2 times tau n. So with these two expressions we will continue studying more about transient analysis in our upcoming lectures. Thank you.